All right, hello, and welcome to my channel. This channel is for educational purposes, and we try to shed light on important theories of everything, all-encompassing theories, uh, difficult, esoteric, and obscure theories that could benefit your life if you knew about them, but you don't because they've been suppressed. And today is our 349th video on the reciprocal system of theory from Dewey B. Larson. And this theory is from the 20th century. Mr. Larson lived from 1898 until 1990. And about 1930, he was, I think, waiting at a stoplight and about to go across the street, and he had this epiphany about a chemistry problem that he is working on, having to do with the interatomic distance. And it had to do with making a few assumptions, and they kind of worked out. And then later he was working on a different problem, and he said, why don't I try applying that same principle to this one? And he got the right answer again. And he applied it a few more times and said, maybe I have some kind of universal understanding here, a key to solving things. And so he spent the next 30 years really developing his ideas. And in the late 1950s, he put out his two fundamental postulates. And from those postulates, he then derived what you would call a theoretical universe. So from those postulates, he deduced a universe as to how his universe would look if his postulates were correct. What would the results be? And then in his books, he basically compared his findings to the findings of the legacy scientists. You know, what did their universe look like compared to what did his look like? And in most cases, his universe looked the same as the kind of the Newtonian universe. But in those relativistic areas, areas of the very small, the very large, and the very fast, the Newtonian system did not agree with Larson's system in the same way that it didn't agree with, some of the new findings that were coming out, that had come out in the late 19th, early 20th century that caused Einstein to propose his theories of relativity and so on. So now, so Larson wrote a bunch of books and many, many articles, gave a lot of talks, and founded a journal, and had a small following. And eventually he died in 1990. After that, some of his small group of followers have carried on and attempted to extend his work and revise it in a certain way. Some were more orthodox than others, but the two that I tend to focus on are Dr. KVK Nehru and Dr. Bruce Peret, who came up with this thing called RS2, and they I believe were in the spirit of Larson's reciprocal system, but they also were able to kind of pick out areas where Larson made mistakes. And Larson admitted that he was, subject to making mistakes. He believed the theory itself was correct, but whether he applied it correctly every time was another question. And if he didn't, eventually it would become clear that he didn't. And so that's what they focused on, and they corrected certain things, or at least made revisions on certain things. One of the things that Dr. Peret changed up is the actual fundamental postulates of the reciprocal system. And so I would like to, this time, read Dr. Peret's fundamental postulates. There are two fundamental postulates, and then unpack them a little bit, and then go into a new article that he wrote, not new, but one that we haven't heard. We've been going through his articles that are entitled RS2-101, RS2-102, RS2-103, and today we're looking at RS2-105. It goes up to 109, so we're going to go through all of those eventually, but today we're looking at 105, but we're going to backtrack just a little bit and go through his fundamental postulates, unpack them, and then get into his 105. Okay, the first fundamental postulate out of two. The first one is by far the more important, but and also I must also add that by using Peret's two fundamental postulates, it gets rid of the need for the metaphysical postulates of Larson. Larson had two fundamental postulates for the physical universe, but then when he started applying those postulates to metaphysical aspects, or things like life and intelligence and ethics, those two postulates did not hold up, and he had to derive four other postulates to encompass the metaphysical realm, like the non-physical, beyond the physical realm. And so, but when Peret does his two fundamental postulates, he no longer needs those four metaphysical postulates because they fit into this other structure that he constructed just by dropping a couple words and adding a couple more. Okay, so the first postulate: the universe is composed of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is that the universe conforms to the relations of ordinary mathematics. Its primary magnitudes are absolute, and its geometry is projective. So that's it. Those are the 2 fundamental postulates. In Dewey Larson's universe, the universe is not made out of matter. It's not made out of energy. It's not composed of fundamental forces. It is made out of motion. And if I were correcting Peret, I would also add scalar motion. The universe is composed of one component, scalar motion, which is a overlooked kind of overlooked variety of motion. Most motion we think of as velocity. It has a magnitude and a direction. Scalar motion is a motion with no direction, which you envision using a balloon with dots on it. You take the balloon and you blow it up. All of the dots are moving away from each other, but they're not moving in any particular direction. Each dot is moving away from each other dot. And in fact, even the areas or locations between the dots are also moving away from other areas or locations between the dots as well. All points on that balloon are moving away from all other points. And the farther away they are, the faster they are moving away from each other. That is a scalar motion. That is a motion that has a magnitude but has no direction. And And that is the kind of motion that, even though the scientists know about that kind of motion, and even though they have observed that kind of motion in the distant galaxies, all of the distant galaxies are moving away from each other, they've kind of relegated that kind of motion to a sideshow, that it's not really that important to know about this, which usually is a pretty good indication that it is a good there is a good reason to know about it. So we've got this scalar motion that Larson has put as fundamental and as central to his narrative, as opposed to the legacy scientists. And this motion comes in 3 dimensions, and in discrete units, and with 2 reciprocal aspects, space and time. So first we'll say the universe is composed of 1 component, motion, scalar motion. And motion, for Larson, is the relationship between space and time. And I might add that motion is also the relationship between time and space. So it could be either. Motion is, space over time, that's speed, but it is also time over space, which is energy. But both space and time, and therefore motion, also come in 3 dimensions. So you can have relations such as time over space squared, which is force, or space over time squared, which is acceleration, or time to the 3rd power over space to the 3rd power, which is matter, and any other permutations or combinations thereof. And you can even get into higher numbers than that if you are using use something like volume. So like density. Density is T to the 3rd power over S to the 6th power, because density is mass over volume. So density is T to the 3rd over S to the 3rd over S to the 3rd, or T to the 3rd over S to the 6th. Okay, so space and time both have 3 dimensions. Larson calls that coordinate time and coordinate space. We are familiar with coordinate space, XYZ coordinates. We're not as familiar with the concept of 3-dimensional time. But as a reciprocal, by definition, 2 reciprocals have the same qualities. So if 3 dimensions adheres to space, it also adheres to time. And conversely, what we know about time is that time is always progressing. It's always getting later and later and later, but in no specific direction. So time is, we see time as being kind of the scalar motion, a motion that doesn't have a direction. And space, therefore, also has that quality. Space is getting farther and farther and farther apart. And we see that in the recession of the distant galaxies. And we also see that in the balloon with dots on it expanding. And then time also is, time and space also come in discrete units, meaning that there's a minimum unit of time and a minimum unit of space. If you don't have a full unit of space, you ain't got space. And if you don't have a full unit of time, you ain't got time. You have to have a full unit. And if you have 1 full unit of space in 1 full unit of time, you have what Larson calls unit speed, or the speed of light. So the speed of light is really the unit of this universe of motion. It is the background, it is the origin, it is the 0 point, the state of rest, which makes sense that in a universe of motion, Even the state of rest is moving. It's moving constantly outward at the speed of light in all directions. Okay, so that's taking a look at the first postulate. The second postulate, the universe conforms to the relations of ordinary ordinary mathematics. He got rid of the commutative part, which Larson had put in there. And its primary magnitudes are absolute, and its geometry is projective. In Larson's system, the geometry was Euclidean, and that prevented a lot of the usages of life phenomena, mental phenomena, that is eliminated when you use projective geometry or the cascade. Euclidean geometry is a subset of projective geometry. And Peret looks at a geometrical cascade. It goes from projective geometry to affine geometry, which is where the life phenomena comes from. Projective is more like this scalar motion level, this all-encompassing universal level. And then affine geometry is life phenomena, metric geometry, and then Euclidean geometry. So Euclidean geometry is just a particular kind of projective geometry. Okay, now let's get started with this this paper here that Peret did on RS2-105. It's called Quantum Pi. And I have to admit that this paper has me a little bit baffled, but I understand the basic idea, and I think it's an important concept, but I don't know that it's totally fundamental to its theory. But we're gonna look at all of them. So we're gonna look at this one. Quantum Pi. Researcher Miles Mathis wrote a couple of interesting papers concerning the mathematical constant pi. What is pi is one of them, and the other one is the extinction of pi, where he causes considerable controversy with his conclusions that pi is an acceleration and has a value of 4.0. Not the conventional 3.1415925. This raises an interesting point in the reciprocal system, because the reciprocal system is based on discrete units of scalar motion, analogous to quanta in conventional science. As you shrink a circle in diameter, eventually you will reach the point where the discrete boundary is reached. Okay, as you shrink a circle in diameter, eventually you will reach the point where a discrete boundary is reached, and you end up with a square instead of a circle. Okay, I'm guessing that he's talking about the discrete boundary of the discrete unit postulate, that time and space come in, and motion, scalar motion, come in only discrete units. And once you get inside that smallest unit, you end up with a square instead of a circle. A unit square has a diameter of 1 unit and a perimeter or circumference of 4 units, making the value of pi to be 4, just as Mathis indicated in his papers, as pi is the relationship between the circumference or diameter and the radius, or circumference or perimeter and the diameter. Sorry. So pi is the relationship between the circumference and the diameter. But if the diameter is a perimeter of a square, then that number actually goes to 4. Upon further investigation into the value of pi, it was found that the answer in the reciprocal system is all of the above, with the caveat that the value of pi is reference system dependent. So he's saying that depending on the reference system that you're choosing, that changes the value of pi. And it can be 4. It can also be 3.1415926. And I would add that, the choice of reference system is fundamentally important in the reciprocal system and with scalar motion. Now, if you go back to your expanding balloon with dots on it, the motion is scalar because it has no specific direction. All of the dots or all of the locations are moving away from each other. But this is only until you choose a reference point. If you arbitrarily decide that one of the dots is motionless, then all of a sudden you have directions between all of the other dots. You can identify the directions that are involved by making the assumption that one of these is motionless, or by saying the same thing in a different way, by choosing a reference point. So when you choose the reference system, then all of a sudden you have directions. All of a sudden you have, if you were kind of going inward, if the balloon were going inward instead of outward, you would have what is called force fields. Okay, so in Larson's system, the reciprocal system, the reference system is very important. Okay, as mentioned in the paper on scalar motion, the units of motion are counting numbers with a minimum quantity of 1. Consecutive units therefore appear as links in a chain, solid bits of metal that can only flex at their boundaries. Larson, during his discussion on direction reversals, states that the only time you can change scalar directions is at the unit boundary, where the links of the chain can bend. This is radically different from the continuum approach of conventional science, where there are no discrete units and the structure is more like a piece of tape, able to bend at any location. Okay, so you're using that chain link idea. The only place that you can bend a chain is at the, if the links of the chain, if there are 50 links of a chain, you can't bend it at any point. You only can bend it at those 50 intersections where it's between one chain and another. Whereas if you had a piece of tape, you could bend it at any point along the way. So the discrete unit postulate means that you only can make those kind of transitions at certain points in between the discrete units. Okay. This section is called pixelation, squaring the circle. In our conventional Euclidean frame of reference, there are 3 orthogonal axes that we divide by fixed distance intervals. In the case of the reciprocal system, those intervals are fixed at one natural unit of space, or time, if we're talking about the cosmic sector, which we didn't get into this video, but if you've watched my videos before, you may know what the cosmic sector is. So, to use an old computer graphics term, our Euclidean reality is pixelated in a fashion similar to what computers draw on a monitor. A bunch of little boxes, not a smooth structure. Pixels have gotten really small these days, but if you take a magnifying glass to your monitor, you will see that it is composed of a bunch of dots of color, and that a diagonal line usually looks like a staircase. It is not smooth. The same happens with curves. They are approximated because the monitor is made of tiny illuminated squares. I also kind of think in this in the same vein as what he's talking about here, maybe with time instead of space, is just the concept of a cartoon. You know, we have a certain resolving power that we can't really go beyond. And if you're, you know, if you look at cartoons, it's a bunch of still photos or still pictures that are viewed in rapid succession, so rapidly that you see a continuous movement. But if you break it down, or if you slowed it down, you would see that you're dealing with a bunch of discrete pictures that are all just slightly different, and that but when put together rapidly, you see it as a continuous movement. It's the same concept here with the chain, and the same concept with the pixelation. You see a diagonal line, but if you put it under a microscope or something, if you expand your vision, then you see that it's pixelated, that it's a bunch of individual dots that are illuminated that do not make a diagonal. They make more of what you would call a stair step, or you know, that it isn't a smooth, you know, isn't a smooth curve. It's a bunch of gradations. So I think it's the same concept here, and Dr. Peret is going to expand it as we move further into this paper. But we are going to stop there right now. I would have to imagine that it's going to take us a few days to get through this paper, because we're going to go pretty slowly to make sure, first, to make sure that I understand it, and then hopefully you will be able to understand it also if we move through this rather slowly, and you know, just kind of go step by step. Peret tends to write. He skips. Sometimes he skips steps. Sometimes he'll leave you behind, because I think he was, you know, pretty much of a scientist, and so if you're not a scientist, you might have to go through this a little bit more slowly, like me. So I hope that I don't go too slowly for you, but if I do, I guess you can just fast forward me. Okay, so thanks for tuning in today. We'll start up again tomorrow, leaving off where we started here, or starting where we left off, actually. And thanks for tuning in. Have a great day.